Bismillah ar-Rahman ar-Rahim. This video is about functions of diagonalizable matrices. If we have a matrix, we can apply a function to it component-wise or element-wise, but this is not what we are talking about here. We are talking about applying a function to a matrix in a very particular way, and our focus will be diagonalizable matrices. Matrix A is an n by n matrix, and its a spectrum or set of eigenvalues are those guys from lambda 1 to lambda k. Matrix A, because it is diagonalizable, then it is similar to a diagonal matrix. We have those eigenvalues living here on the main diagonal of matrix big lambda. And then there is the matrix Q, whose columns are the eigenvectors of matrix A. And this is the inverse of matrix Q. Let's partition the columns of matrix Q into G1, G2, all the way to Gk. Gj is a matrix. Of course, the number of rows is equal to n, which is the size of matrix A. And then how many columns do we take? The algebraic multiplicity of the eigenvalue lambda j. Because the matrix is diagonalizable, then the algebraic multiplicity is exactly equal to the geometric multiplicity. The columns of Gj are basically the vectors spanning the eigenspace associated with the eigenvalue lambda j. This is the diagonal matrix of eigenvalues. This is big lambda. Lambda 1 will appear repeated a number of times equal to the algebraic or geometric multiplicity. The same for lambda 2 and so forth. As we did to matrix Q, we also partition matrix Q inverse. So the first AM of lambda 1 rows, those will be matrix B1. Then the next AM of lambda 2 rows will be the matrix B2, and so on. Matrix A is Q lambda Q inverse. Defining the G's and the B's, we can write matrix A as lambda 1 G1 B1 plus lambda 2 G2 B2 all the way to lambda K GK BK. Let's define EJ to be GJ BJ, and it is an n by n matrix. Again, what we have here is that GJ, this is a matrix of size n by the algebraic multiplicity of lambda j. Then BJ is of size the multiplicity of eigenvalue lambda j by n. Their product will be an n by n matrix, and this is EJ. We can write down matrix A as lambda 1 times E1 plus lambda 2 times E2 to lambda k times EK. How do we apply the function to the matrix? We simply apply it to the eigenvalues. If we look at this representation for matrix A, then the function f applied to matrix A, so this is the function applied to an n by n matrix, and the output is an n by n matrix, is Q, and then we apply the function to the eigenvalues of the matrix. Here on the main diagonal, we have f of lambda 1 repeated a number of times equal to the multiplicity of lambda 1, and then f of lambda 2 repeated a number of times equal to the multiplicity of lambda 2, and so on. And then we have Q inverse. The function applied to the matrix means that we apply the function if we can, because it may be that as a function to R, the function has a restricted domain. Its domain, it's not the full set of real numbers. So perhaps we have the square root function and its domain is the set of non-negative real numbers. But matrix A, it may have negative eigenvalues. Be able to apply the function to the matrix in this way, it must be the case that the eigenvalues of the matrix are in the domain of the function. F applied to a diagonal matrix means that we applied element-wise to elements on the main diagonal of the diagonal matrix. F applied to diagonalizable matrix A means that we construct this matrix here that is obtained from the eigen decomposition of matrix A. If A is Q lambda Q inverse, then F of A, which is another n by n matrix, is Q on the left, Q inverse on the right. That's fine. But then what we do is that we visit the diagonal matrix big lambda, and on the main diagonal, we replace each lambda by F applied to the eigenvalue lambda. The off-diagonal elements will remain zeros. This is how we define the function applied to the matrix. If we go to the second representation of matrix A using those E matrices, then f of A is f of lambda 1 times E1 plus f of lambda 2 times E2 all the way to f of lambda k times EK. Note that the E's will not change because those come from matrix Q and matrix Q inverse. And the way that we define the matrix function does not alter Q or Q inverse. What it changes is the diagonal matrix of eigenvalues. In this video, the main thing that I want to talk about is this. All matrix functions, if defined, are polynomials, which means that if there is a function that we can apply to the matrix A, then this function can be represented as a polynomial in A. So it will be a bunch of scalar coefficients multiplied by the powers of A. This is something peculiar to matrix functions. Let's show this result by first investigating the E matrices. Note that the E matrices come from Q and the inverse of Q. By definition, Q inverse is identity, and Q inverse Q is also identity. Let's take this form here. Q is G1, G2, all the way to Gk. Q inverse is B1, B2 to Bk. Now, if we multiply, we have G1 times B1 plus G2 times B2 all the way to Gk times Bk. This sum is equal to identity n by n. Now, G1 B1 is E1, G2 B2 is E2, and so forth. This means that the sum of the E matrices is equal to identity. This is the first observation that comes from the way in which we defined the E matrices using the G and B matrices. The sum of the E matrices is exactly equal to the n by n identity matrix. We also have that Q inverse Q is equal to identity. Let's see where this can lead us. B1, B2, all the way to Bk. This is Q inverse. Now let's multiply by Q. This is G1, G2 to Gk. This is also equal to identity. If we do this product, then we get a matrix, and this matrix is n by n. The block that we have here is B1 times G1. Let's remind ourselves of the sizes. B1 is a matrix with a number of rows that is equal to the multiplicity of the eigenvalue lambda 1. And then the number of columns is equal to n. So this is the multiplicity of lambda 1 by n. G1, on the other hand, is n by the multiplicity of lambda 1. This block is a square matrix of size the multiplicity of lambda 1 by the multiplicity of lambda 1. Then the block that we have here, this is B1, G2. Now for this block, the size is the multiplicity of lambda 1 by the number of columns of G2, which is the multiplicity of lambda 2, and so on. This matrix here that we can construct by carrying out this product is equal to identity. The conclusion is the following. EV times GL. This is a matrix with a number of rows equal to the multiplicity of eigenvalue lambda V, and the number of columns equal to the multiplicity of lambda L. So I need to correct this one and write L here. If L is equal to V, then we have identity. If the two indices are not the same, we get an all-zero matrix. Now let's proceed to deduce some of the properties of the E matrices. Suppose that we study EV squared. EV times itself. Now EV is equal to GV BV and then GV BV. On the previous page, we have discovered that if we take a B matrix times the respective G matrix, then we get identity. So this is identity, and we have GV BV. And GV BV by definition is the matrix EV. The conclusion is that EV squared is equal to EV. EV is an idempotent matrix whose square is equal to itself. This means that EV is a projector. It is a projection matrix. What will happen if we multiply two E matrices with a different index? Let's take EV by EL. Now V is not equal to L. EV is GV BV. EL is GL BL. Here in the middle, we have BVGL, and V is not equal to L. This is an all-zero matrix. So the overall result will be that we get an all-zero matrix of size n by n. Therefore, EV, EL, this is EV if L is equal to V, and this is the all-zero matrix if L is not equal to V. Let's investigate this particular matrix, A minus lambda V times identity. A itself can be written as this sum. This identity matrix here can be written as the sum of the E matrices. Recall that on the previous page, when we studied the multiplication of Q inverse, and we said that this by definition must give us identity. Q, it has those G matrices as columns, and Q inverse, it has the B matrices as rows. And this means that G1 B1 plus G2 B2 all the way to GK BK is identity. And so the sum of the E's is identity. What we do here is to rewrite the identity matrix as a sum of the E matrices. Combine the two sums. This will be from L to K, and then we have the matrix EL. And here we have the difference, lambda L minus lambda V. We can write down A minus lambda V times identity as a summation L from 1 to K. Lambda L minus lambda V, this is scalar, is multiplied by the n by n matrix EL. Note that if the index L is equal to V, then what we have here is 0. We can write down this sum, excluding the case in which L is equal to V, because we have 0 multiplied by EL. A minus lambda V identity, this is summation L from 1 to K, L not equal to V, not equal to this index here, of the scalar quantity lambda L minus lambda V multiplied by EL. Let's now consider a product of those matrices. The product will be over the index V. I will take a product of A minus lambda V times identity, where V is from 1 to K, but we exclude J. We will choose J, so J is in the set from 1 to K, and we exclude its value from the set of possible values of the index V. This is the product. And now from the previous line, we know that A minus lambda V times identity can be written as this summation here. Let's think carefully about this product of a sum. We have brackets. Each bracket contains a sum of the E matrices. Each one is multiplied by scalar. And then we multiply those brackets. Note that when we do so, we have this very nice result. We multiply two E matrices and their indices are distinct. Then the product is the all-zero matrix, which means that when we multiply the brackets, many results will be the all-zero matrix. What will be the surviving terms? To be concrete, let's assume that K is equal to 3. and that we choose j to be equal to 1. On the left-hand side, we have a minus lambda 2 by identity times a minus lambda 3 by identity, like this. We don't have a term with lambda 1 because the index of our product does not take the value 1 in this particular example. What is more important is the right-hand side. When v is equal to 2, this means that the summation will be L from 1 to 3, and L is not equal to v. So L is not equal to 2. The first bracket will be lambda 1 minus lambda 2 times E1. L cannot take the value 2, but then it takes the value 3. If L is 3, we have lambda 3 minus lambda 2, v is equal to 2. And then here we have E3. If v takes the value 3, which is k in this example, we have here lambda 1 minus lambda 3, E1 plus lambda 2 minus lambda 3, E2. Let's multiply E1 by E2 or E3 by E1, E3 by E2. All these give the all zero matrix. The only surviving term is lambda 1 minus lambda 2, lambda 1 minus lambda 3, E1 squared, which is E1. What do we learn from this example? We have a product of sums, a product of brackets. Each bracket will contain EJ. Each bracket is indexed by V. V does not take the value J. L does not take the value V. For every value of V, L will assume the value J. We are sure that in each one of those sums, or in each one of those brackets, we will have EJ. And then we will have E's with an index that is not equal to V. Because of this property of the E matrices, the only surviving term will be, in the general case, when we take EJ from each bracket, from each sum, and multiply those terms together. Otherwise, we will have a product of two E matrices with distinct indices, giving us the all zero matrix. Based on this investigation, we have the product V from 1 to k, V is not equal to J. We don't really need to write down a sum. From each sum, the relevant term is lambda J minus lambda V times EJ. If we carry out this product, we get product V from 1 to k, V is not equal to J, lambda J minus lambda V, and then EJ is multiplied by itself, k minus 1 times. But EJ is an idempotent matrix, so we have EJ here. Product V from 1 to k, V not equal to J, A times lambda V identity. This is equal to product V from 1 to k, V not equal to J of lambda J minus lambda V. This is multiplied by EJ. The eigenvalues are distinct, so this is a non-zero quantity. And now we can write down EJ as this product divided by this scalar. This is our result for EJ. If we expand this product, we will get powers of matrix A, and the highest power is k minus 1. EJ is a polynomial function of matrix A. The function f applied to matrix A is f of lambda 1, E1, plus f of lambda 2, E2, and so forth. It's a summation j from 1 to k, f of lambda j. EJ. And now we know that EJ contains powers of A all the way to k minus 1. This means that the function f of A is a polynomial function in the matrix A. It can be expressed as a finite linear combination of the powers of matrix A. Let's do an example. A here is a 3 by 3 matrix. Here is the characteristic polynomial, lambda minus 1 times lambda plus 3 squared. If we equate this to 0, then A has two distinct eigenvalues, 1 with multiplicity 1 and minus 3 with multiplicity 2. We have two distinct eigenvalues. This means that k is equal to 2. In the expressions for the E matrices, we have in our example E1 and E2, we need to compute A minus lambda 1 identity and A minus lambda 2 identity. Here they are. This is the case when the eigenvalue is 1, and this is the 3 by 3 matrix that we obtain if we compute A minus lambda 2 identity and lambda 2 is minus 3. What are the E matrices? We have a product, but because in our example here, k is equal to 2, and in each product there is an excluded term, then actually each product has one term. Recall that EJ is equal to 1 over the product V from 1 to k, V not equal to J of lambda J minus lambda V. Now k is equal to 2, and if we take J to be equal to 1, then the possible value of V is 2. So what we have here is lambda 1 minus lambda 2, 1 minus minus 3. And then this scalar is multiplied by the matrix A minus lambda V times identity. V again goes from 1 to K, which is 2, and V is not equal to J, which is 1. So V has only one value, which is 2, and lambda V is minus 3. E1 is equal to 1 over lambda 1 minus lambda 2. This is the scalar, which is 1/4. And then we have 1 plus 3 times identity, which is this matrix here. And this is E1. For E2, now J is 2 and V is 1. So this will be lambda 2 minus lambda 1, minus 3 minus 1. And this product, in the second case, will be A minus lambda 1 times identity, which is this matrix here. This is E2. A function f of A is equal to f applied to the eigenvalue 1 times this matrix, which is E1, plus f applied to lambda 2, which is minus 3, and this is the matrix E2. If we write down things explicitly in terms of the A matrix, the original matrix, then this is f of 1, and this is E1, 1/4 times A plus 3 times identity, plus f of minus 3, and this is E2, which is minus 1/4 times A minus identity. As we can see, that f of A is a scalar times A plus a scalar times identity matrix of size 3 by 3. This is the whole point in this video, that functions of matrices, and here our focus was diagonalizable matrices, are polynomials, in the sense that you take a function and it can be represented as a finite sum involving the powers of the matrix. If f is the exponential function, then f of 1 is e to the power 1, and f of minus 3 is e to the minus 3. And this is e to the power a. It is polynomial in A. And these are the elements of the 3 by 3 matrix e to the power a.